Are you stuck trying to understand the different types of error and significance tests? Type 1, type 2, did I do it, did I not? Well, you've come to the right place because in this video we're going to tackle exactly that topic. Let's just dive right into it by actually looking at an example. I believe the best way to understand error in significance testing is to see it through the eyes of a specific problem. So here is our first scenario. A recent report claimed that 14% of United States teenagers vape. Jillian senses that vaping is a much larger issue in her hometown, which is a fairly large suburban city. To test her beliefs, she gave a sample survey to a sample of 75 random teenagers from her city, and 21 noted that they vape. Is this evidence that Jillian is correct and that a higher proportion of teenagers in her hometown vape? Now, we believe the national truth is that 14% of kids vape, but her sample revealed 21 out of 75, which is 28%. So the question that Jillian has to figure out is this 28% significantly larger than 14%? I mean, obviously it's larger than 14%, but is it so significantly larger that we should go ahead and deem that this is solid evidence that she is correct and that students in her city vape more often? All right, so let's actually just dive right at it and just look at the results here. So this is the statistical analysis of this. So our null hypothesis, of course, is that the truth is 14%. We're going to assume that what we read is true. And our alternative is that it's greater than 14%, the proportion of kids in her city that vape. Now, we built the sampling distribution. We found the mean. We found the standard deviation. The shape is, of course, normal. We checked all of our conditions. This is awesome. And, all right, this is a model that shows us all possible p-hats of size 75 taken from this population. Now, her sample, if you recall, was 28%. 28% is way up here. That was her beautiful and one and only one p-hat. And then we say, okay, well, how likely is that sample? It does appear by the eyes, by the z-score, 3.491, to be significantly high. But it's that p-value that really hits home. The p-value is the probability that of all those possible sample proportions, one would come back even more extreme than Jillian's 28%. And that gave us a very low p-value. And with a very, very low p-value below our level of significance, let's just say we're using 5%, we would reject the null. There is significant evidence that the proportion of teenagers that vape in Jillian's city is more than 14%. Okay, great results of a significance test here. But let's play a little game I like to call the what if game. What if she were to replicate this? Looking at another sample of 75, and then another, and another, and another, and another, and another. Look at, there's millions of samples of 75 teenagers from her large town. Let's analyze that. So let's just say that she looked at another sample and it came back right around here, actually a little bit below 14%. And maybe another sample came back here, another sample came back here, here, a couple samples below, and some samples a little bit above, but not significantly above, right? And let's just say that after she did many more samples, she replicated this situation of randomly surveying 75 teenagers from her town. She found out that, well, all of these other samples would have caused her to not reject the null. And if you think about it, if all of those samples, I mean, if there's really that many samples that were close to 14%, we would actually maybe confirm that 14% is actually true. Now, what would that mean about what we did here in this actual problem? Well, that would mean that Jillian was actually wrong. She just so happened to get this one really, really high p-hat that produced a really, really low p-value, and it just so happened that she got a sample that told her to reject the null. But that was the wrong decision. All of the other possible p-hats, if she were to replicate this, would have actually told her that 14% was true. Well, this would mean that the results of her original sample was an error. This brings up what we call type 1 error. A type 1 error occurs when the null hypothesis is in actuality true, but we reject it and believe that the alternative hypothesis is true based on a sample proportion. Again, it's called a one sample Z test. We only looked at one sample. And what if that one sample told us to reject the null hypothesis, but in actuality, that null hypothesis was true. In our criminal court analogy, right, in the American criminal court system, this would be like sending an innocent man to jail, right? He was innocent, but there was that one teeny weird piece of evidence that made us think that he was guilty, so we sent him to jail, but the truth was he was innocent. Now, obviously, this is making the wrong decision here, okay? And we don't want this to happen, but the point I'm trying to make to you is anytime we reject a null hypothesis, let me repeat this one more time. Anytime we reject a null hypothesis, there is the possibility that we were wrong, and that null hypothesis is actually true. And the reason why there is potential for this, and again, obviously I hope this doesn't happen, but the reason why there's potential for this is because what if we get that one really weird sample like this one that told us to reject the null? We did all of the correct math work. We didn't do anything wrong in our math work, but all other possible p-hats, if we were to replicate taking samples of teenagers from Jillian's town, would have told us otherwise. And all those other samples would have basically confirmed that the true proportion for her town was 14%, but we concluded otherwise. Again, it's a type 1 error. You don't have to stress about, did I do it? Oh my gosh, this isn't an error that you made. It just means that your one sample led you to the wrong decision. Now, let's kind of further explain this a little bit. Now, let's think about what I call the rejection zone. The rejection zone is the area that a sample would have to fall for you to reject the null. Now, I mentioned that we were using an alpha of 5%. Now, that would mean that the top 5% of p-hats would cause me to reject the null. So if you have a TI-84 calculator, you could get this, or you could use one of your tables, your Z tables. But the top 5%, which is equivalent to the bottom 95%, falls at the 1.645 Z-score. A Z-score of 1.645, so right about here. That's a Z-score that has 5% above it. That means any sample falling in that top 5% probability would cause us to reject the null. Okay, so the point I'm trying to make is that 5% is not impossible. I mean, it could happen. So if all other samples were around 14%, which again would confirm that 14% was true. So if that's what was actually true, 14% was true, the true proportion of kids in her town that vape is 14%, there is a 5% chance that we get a sample in the rejection zone that would tell us that 14% is wrong. So that actually leads me to the idea that the probability of making a type 1 error is your level of significance. So you actually kind of choose your level or your probability of a type 1 error. When you choose 5%, you are now running a risk that you have a 5% probability of having a type 1 error occur. It is what it is. Now, obviously, one thing we could do, this makes a lot of sense, is we could reduce alpha. We could lower alpha. That will reduce our chance of making a type 1 error. Now, when reduce alpha, you're being more strict. This means now to reject, I'm going to go with 1%. So if I make my alpha 1%, 0.01, that means that I'm going to now have to increase my rejection Z-score. So again, if you grab a table or grab your TI-84 calculator and do an invert norm of the bottom 99%, the top 1%, that's a Z-score of 2.326. So somewhere right around here would be the rejection zone, 2.326. That's a Z-score of 2.326 or higher would cause us to reject. So one thing that we could do to try to reduce this probability of a type 1 error is decrease our alpha, which makes the area of which we would reject less likely. And if the truth, again, this is all on the assumption that the truth is really 14%, then now I'm less likely to get a sample that would tell me that 14% is wrong and cause me to reject it. So again, type 1 error happens anytime, doesn't happen anytime. It potentially could happen when you reject the null. When you have a conclusion like we did here, and the conclusion are 28% at a very high z-score that had a very low p-value, that told us to reject the null. Anytime that happens, you're only basing that decision off of one sample, so there is the possibility that we were wrong, and that the truth was actually 14%, and we should have kept the null, essentially. Now, what are you going to do? Don't worry about did I make it, did I not make it, right? No one's ever going to ask you, did you make a type 1 error? Because you will never know. You're doing what you know to do based on your one sample. I'm just trying to explain that if we did have a ton of resources and a ton of time to replicate, then maybe we could actually see that we were wrong. All right, now let's look at actually the opposite of this issue with scenario number 2. Recent report claimed that 14% of United States teenagers vape. Jillian senses that vaping is a much larger issue in her hometown, which is a fairly large suburban city. So to test her beliefs, she gets a survey of 75 random teenagers, and 13 said that they vape. So once again, she believes, or she read, that 14% is the truth, but her sample, she's wondering, does her sample give that significant evidence that it's more? Her sample showed 13 out of 75 that vape. That is 17, a little smidgen over 17%, about 17.3%. So once again, Jillian has to answer the question, is that just a little bit higher that it happened due to just random variability, or is it significantly higher? So let's look back at our sampling distribution here. Same null, same alternative hypothesis, same mean, same standard deviation, but now her sample came back right about here. A z-score of 0.823, that would be the z-score for her p-hat of 0.173. And again, what would we do with that p-hat? Well, we would, it has a very high p-value, meaning that a sample or like that or more extreme is actually very likely. And this would cause us to fail to reject the null. So Jillian's going to say, well, I guess I don't have enough significant evidence to claim that the proportion of teenagers in my town vape more than 14%, who vape is more than 14%. But same thing I kind of did last problem. What if we went ahead and did some replication by saying, all right, we got a lot of resources here. Let's look at multiple more samples. And let's just say another sample comes up here. Another sample comes back 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 here. And sample after sample after sample actually show that Jillian was wrong and that she should reject the null. But her one sample, because her entire test was based on one sample, told her to fail to reject the null. But again, what if that was wrong? What if the truth was that the alternative is correct and that the true proportion of kids in her town that vape is greater than 14%? Okay, so the only way we would, again, same thing I mentioned earlier. Did she know about this? Well, no, it's not an error in her math work. We're just saying that if she had the resources to do the replication, then she could possibly see that all other possible p-hats would be way above 14%, so high that we would reject the null. But she just so happened to get that one sample that told her to fail to reject the null. Now, this is what we call a type 2 error. A type 2 error occurs when in actuality the null hypothesis is false and the alternative is true, but we failed to reject the null. So any time, and I mean any time, you fail to reject the null, you are at risk for a type 2 error. Because you're like, man, I failed to reject the null, but what if I'm wrong? What if, in actuality, the alternative is really true? Now, please, I want to say this one more time. I'm never going to ask you, hey, did you make a type 1 error? Did you make a type 2 error? You're never going to know. You are doing the work that you were taught. You are making the decision based off of one sample. That's why it's called a one sample z-test. But the idea is if we had those extra resources to replicate many, many, many more times, and we found out that, oh my gosh, all other samples would tell us to reject the null, that means their null is wrong, and it is more than 14%. She just so happened to have this one sample that told her the wrong decision. It's okay. Anytime you fail to reject the null, you are at risk for a type 2 error. So once again, let's talk about that rejection zone. That 5% rejection zone starts at a z-score of about 1.645. Anything up here is going to tell her to reject. So what is the probability of a type 2 error? Well, don't worry about calculating it, right? But it's called beta. Okay, it's called beta. You're never going to be asked to calculate. It's outside the scope of at least this course. Now, the idea though is this. Just think about this. If the truth is that the null is wrong and that the 14% is incorrect and that the truth is that it's really higher than 14%, then if I really wanted to reduce type 2 error, then what I should do is increase my alpha. So maybe we make alpha 7% or 8% or even 10%, which I would never necessarily recommend. But what happens is then what you're doing is you're making the rejection area bigger. And if you make that rejection area bigger, then you're more likely to get a sample that's going to tell you to reject the null. And if that's the right thing to do, rejecting the null because the alternative is correct, then that's what you should do and that would work. So now we kind of have this issue here where alpha is type 1 error, beta is type 2 error, and I just got done saying with type 1 error, lower your alpha. Lower your alpha, you will reduce type 1 error. But if I lower my alpha, that's going to increase type 2 error. And then if I say, well, okay, I don't want type 2 error, so I'm going to increase my alpha, giving me a higher rejection area, which is going to cause me to be less likely to make a type 2 error, then I'm actually more likely of making a type 1 error now. So I know there's a little bit of a give and take here, but just have to understand that the idea is simple. We're trying to make a decision with one sample. And when you make a decision with one sample, you might be wrong. You might be getting a one sample that's just a weird sample that told you to do the wrong thing. This is not a mathematical error. This is not something that you have to worry about, did I do or not do. It's just the possibility of it is there. It is out there. Now, the bigger issue, and I don't want to say the bigger issue, but think about it this way. Like in any significance test, it would only make sense that we're looking for the alternative to be true. I mean, no one does research hoping they're wrong, right? If Jillian didn't think that more kids or a higher proportion of teenagers in her city vaped, then she wouldn't have even been doing the test in the first place. So we're always looking for the significance test to agree with us. We're always looking for the alternative to be true. So if the alternative really is true, we should reject the null. Now, this is where we introduce you to this word called power. Power is the probability we correctly reject a null hypothesis that is false. If the alternative is truly true and the null is wrong, we should reject the null and conclude that the alternative is true. Doing that, that's called power. The probability of doing exactly that is power. Now, I know we might use that word power all over the place in the English vocabulary, but in statistics, power is actually a really good thing. It is the probability of correctly rejecting a null hypothesis that is false. So, the power of a test is actually the complete opposite of a type 2 error. Okay, remember a type 2 error is beta. The type 2 error is, oh no, I made a mistake. The null was wrong, but my conclusion was to fail to reject it. Think back to what Jillian did right here. Her sample ended up being 17.3%. Her sample ended up having a very high p-value, so she failed to reject the null, but that was wrong. That was wrong. So this would be a type 2 error. Power would be getting one of these samples. So power would be getting one of these samples that would actually agree with my alternative that the true proportion of teenagers that vape is more than 14%. So power is a good thing. We always want more power, and power is going to be the opposite of type 2 error, which is getting rid of it. Now, you might say, well, what about this whole idea of, okay, how do I get more power? Okay, well, that's actually a great question. Let's just stop right there for a second. How do I get more power? Well, it's actually really common sense. We want more power because if the null is wrong, we want to correctly conclude that. So how do you get more power? Number one, makes so much sense. Increase your sample size. Bigger samples will be closer to the truth. And again, if the truth is that it's way above 14%, then a bigger sample is going to allow me to see that. Now, I hope you know that bigger samples vary less, which means a bigger sample will produce a standard deviation that's smaller. And that means more p-hats will be closer to the null hypothesis. And you say, well, wait a minute, if more p-hats are closer to the null, then how am I going to see that the null is wrong? Well, this is why a bigger sample will work. Because if more p-hats are near the truth, but remember, if the truth is that the null's wrong, then you'll be more likely to see those samples that are close to the truth, which is further from the null hypothesis. So you might have to take time to process that. But again, bigger sample size, simply put, are going to reveal the truth more likely, right? Like if you only got a sample of 5 kids, who knows what you're going to get? Just get a sample of 500 kids, you're going to be closer to what's true for all kids. So that's why bigger samples are going to be more accurate and get you to the truth. Now, the next thing you could do to get more power is to increase the significance level of your tests. And again, this might take a moment to explain, but I'm going to do my absolute best to do so. So if I increase alpha, okay, I am lowering type 2 error, which is beta. And if I'm lowering type 2 error, which is beta, I'm increasing power, because remember, power is the complete opposite of type 2 error, which is beta. Now, why does this work? Because if I move my rejection zone up by making my alpha, let's just say I go from an alpha of 1%, which is again a z-score of 2.326, and I say, you know what, I'm going to use an alpha of 0.05. That's going to move me up to 1.645. So if I increase my rejection area, this gives me more reason to reject the null. And if that's what I'm supposed to do, because the null is truly wrong, then having a larger alpha is going to increase my rejection area, which is going to make it more likely for me to find a sample that's going to cause me to reject the null. And if I reject the null, and that's the correct decision, I'm reducing type 2 error. And if that's the correct decision, I have more power. So increasing alpha does give you more power, but I would be very cautious to increase it too high, because then you really run risk of a type 1 error. But actually, if you think about it, if a type 2 error, if power is the null's actually wrong, so I'm not even worried about a type 1 error in that situation, because if in a type 1 error, the null is true, but if I'm like, no, the null's wrong, then I'm not even worried about a type 1 error. So again, that's why increasing alpha will increase your power. Now, the last thing to do is kind of weird, because it's actually not in my control, but it does work. When the actual truth is further from the null, hence our sample statistic could be as well, you would have more power. Okay, let me explain this again with an example. Let's just say that the true proportion of kids in Jillianstown that vape is 35%. That is way, way, way above 14. I mean, that's way over here. Now, if that really is true, and I take samples from Jillianstown, guess what? My samples will also be very close to 35%. Now, they're not going to be exactly 35% because samples vary, but if the truth is really far from the null, then my samples should reveal that more easily. And then I would reject the null and go with the alternative. Oh my gosh, it makes so much sense. So again, when the actual truth is further from the null, it's going to be easier for me to see that. Now, let me give a counterexample to this. Let's just say the truth was 16%. Now listen, 16% is more than 14%. There is no doubt about it. My alternative is true. More than 14% of kids vape in Jillianstown, even if it's 16%. By definition, it's more. But the problem is, that means I'm going to get a lot of samples that could actually be even, still around 16%, but they're so close to 14% that I might use one of those samples like this one that's going to actually cause me to fail to reject the null. So the idea here is the truth is still that it's more than 14%, but if the truth is only a little bit more than 14%, my samples might not show me that, and then all of a sudden I'm failing to reject the null, and I'm like, man, I should be rejecting the null. Okay, hopefully that makes sense as well. Now, the only issue with that that possibility right here is that that's kind of out of my control. Like, I can't control what the truth is. I certainly don't want to be biased. I don't want to go fishing or for the answers I want. That's completely um, illegal in the world of statistics, right? For lack of a better word there. So again, quick recap. How do I get more power? Increase your sample size or increase your level of significance, okay? That's going to give you more power. And power is doing the right thing. The alternative is true, and you conclude that. The opposite of that is type 2 error. Type 2 error is when, you did what Jillian did. She thought she was doing everything right, and she did. She didn't do anything mathematically wrong. She just happened to get this sample that told her to fail to reject the null, but in actuality, she should not have done that. And then again, don't also forget about type 2 error. Type 2 error is when your conclusion is to reject the null, but the null was actually correct. It was actually correct. You just happened to get this one sample that told you otherwise. So at the end of the day, you can't make both a type 1 and a type 2 error in the same problem. That just doesn't make sense. But if you reject the null, you are at risk for a type 1 error. If you fail to reject the null, you are at risk for a type 2 error. Those are some questions that you could definitely be asked. But at the end of the day, we obviously want to avoid error at any cost. Bigger sample size will always help get rid of any type of error and give you more power to see what's clear. But the only thing I want to leave you last with here is don't go fishing, right? Don't go fishing, right? If you think about this idea of repeated sampling, right? Now, everything I'm teaching you right now is all based on one sample. But, if we were to go ahead and get sample after 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 sample, and all of those samples came back so close to 14% that the only logical thing we should do is fail to reject it. Maybe 14% is correct. But then there was that one sample way over here. It would be completely against all facets of statistics to purposefully use this sample. That way you could reject the null and say that you're right, but all of your other samples pointed you otherwise. That would just be immoral, right? That would be so bad. So, all right, don't ever do that. Use the procedures I've taught you. Make the decision based on how I taught you, and then just cross your fingers, right? At the end of the day, you're never going to know if you made a type 1 error, type 2 error. You just have to know that the possibility of them exists. All right, that's it. That was a longer video, but there's a lot going on with this idea of error, and I hope it all makes complete sense.